Now, for cellular respiration, there are a couple of things that we need to know. First of all, would be the definition of catabolism and anabolism. So, for catabolic, meaning breakdown of larger molecules to smaller one, while anabolic means putting together smaller molecules into bigger ones. On the other hand, when we talk about exergonic and endergonic reactions, we mean by exergonic that there's a release of energy, while in endergonic there is absorption of energy from the surrounding. So we're very familiar with this. Cellular respiration is catabolic, while cellular respiration is also exergonic. So those will be the characteristics we would need to take note of. So catabolic and exergonic, and cellular respiration is defined as the breaking down of organic molecules to produce ATP, which is the energy currency of the cell. Now, there's another term we have to take note of, which is aerobic and anaerobic respiration. Very familiar with us. When we talk about aerobic respiration, it is simply respiration with oxygen, while anaerobic respiration is respiration without oxygen. So here's an example of that. When we can't breathe, or we have difficulty breathing, or unable to breathe, any kind of situation will proceed towards anaerobic respiration, because there is the absence of oxygen here. So for example, while running, we have difficulty breathing. So this means that because of the less oxygen going into our lungs, this will cause our muscles to undergo anaerobic respiration. So when the oxygen in our lungs is absent or less, anaerobic respiration can happen. But if you are breathing normally, then you will have aerobic respiration. In addition to that, these are some examples of anaerobic respiration, like Swiss cheese, wine, vinegar, soy sauce. So we talked about that last time. So these are produced without oxygen, or term to be fermentation on anaerobic respiration. We'll be talking about that a little bit later. Now, other things we have to talk about is that cellular respiration is also a redox reaction. So do take note that glucose becomes oxidized into carbon dioxide, while oxygen becomes reduced to water. So that's why it is also a redox reaction, just like photosynthesis. So again, glucose is oxidized to carbon dioxide, while oxygen is reduced to water. So that's an important concept. It's an oxidation reduction reaction. Now let's go straight to the 4 stages of cellular respiration. So that's glycolysis, pyruvate oxidation, Krebs cycle, and oxidative phosphorylation. So GPKO, glycolysis, and Krebs cycle and oxidative phosphorylation are the major stages, while pyruvate oxidation will be intermediary between glycolysis and Krebs. Nevertheless, there will be 4 of these stages: glycolysis, pyruvate oxidation, Krebs cycle, and oxidative phosphorylation. Now, in which part of the cell does glycolysis takes place? Well, you know this already. The answer is it happens inside of the cytosol or cytoplasm. While another question, which stages of cell respiration happens in the mitochondria? So you already know that it will be the pyruvate oxidation, Krebs cycle, and oxidative phosphorylation. So showing you this picture, this will show us that outside of the mitochondrion, glycolysis will be happening, while inside of the mitochondrion, the pyruvate oxidation, citric acid cycle or Krebs cycle, and electron transport chain etc. and chemiosmosis will be happening also inside of the mitochondrion. Now, since we're showing already the ATP, glycolysis produces 2 ATP, Krebs cycle, citric acid produces 2 ATP, while most of the ATPs will be produced by the electron transport chain or oxidative phosphorylation, chemiosmosis. That will be around 26 to 28 in our SLG. For this picture, it's around 32 ATPs. Nevertheless, most of the ATPs will be produced by ETC or the oxidative phosphorylation. Okay, now other things we have to take note of here is that this ATP in glycolysis is said to be substrate level phosphorylation. Citric acid Krebs cycle ATPs produced is also substrate level phosphorylation, while the ATPs produced through the electron transport chain chemiosmosis is said to be oxidative phosphorylation. Now, the reason for that is because this ATP comes from a substrate, which is glucose pyruvate, while the ATP here would be coming from a substrate, which would be the intermediary molecules of the citric acid cycle or Krebs cycle. That's why these both would be termed as substrate level phosphorylation. On the other hand, this is not substrate level because there is no substrate from which phosphate can be taken out of, but rather the NADH and the FADH2 would be producing the ATPs through chemiosmosis. We'll discuss that a little bit later. Just remember it's related with H plus going through the ATP synthase, and we'll see that a little bit later. Okay, so again, what is the difference of substrate level and oxidative phosphorylation? Both of them produce ATP. The substrate level phosphorylation occurs because phosphate is directly transferred from a substrate like pyruvate, and then oxidative phosphorylation is based on electrons moving through the ETC. Okay, so that will be the answer to that. So again, you will see here the two ATPs in the citric acid cycle and 26 to 28 ATPs in the oxidative phosphorylation. We'll go into details. Now, looking at this picture, we have discussed this in class. This will be easier for us to take note of. So we start off with glucose that happens in glycolysis. So glucose will be separated into two molecules of pyruvate, a 6-carbon that will be broken down into two molecules of 3-carbon pyruvate, and doing so you need 2 ATP, or you use 2 ATP. Then you produce 4 ATP, which is a net of 2 ATPs here, and then you produce NADH. So for glycolysis, you will produce 2 ATP and 2 NADH. Okay. After that, the pyruvate will enter the pyruvate oxidation, wherein pyruvate, which is a 3-carbon molecule, now becomes 2-carbon molecule called acetyl-CoA. So this means the pyruvate will release carbon dioxide and the other pyruvate will release carbon dioxide. Therefore, there are 2 carbon dioxide that are released during pyruvate oxidation, as you can see over here. In addition, 2 NADH will be released also in pyruvate oxidation. After that, the 2-carbon acetyl-CoA will now enter into the Krebs cycle. First of all, it will combine with the 4-carbon molecule, therefore becoming 6-carbon molecule, and it will go back to becoming 4-carbon molecule. In doing so, the 6-carbon becoming 4-carbon will release carbon dioxide, NADH, ATP, and FADH. Now take note, 1 acetyl-CoA will produce 2 carbon dioxide, 3 NADH, 1 ATP, and 1 FADH. But since there are 2 copies of this acetyl-CoA, it now becomes times 2. That's why 2 times 2 is 4 carbon dioxide, 3 times 2 is 6 NADH, 1 times 2 is 2 ATP, and 1 times 2 is 2 FADH. That's why you will have in the Krebs cycle 2 ATP, 6 NADH, 2 FADH2, and 4 carbon dioxide. So at this point, without entering yet the oxidative phosphorylation, you now have a total of 4 ATPs produced from glycolysis towards the Krebs cycle, and these 4 ATPs are the what we call as the substrate level phosphorylation. However, it doesn't end there, because you will be using NADH and the FADH, all of this, to produce ATP, and that will be through the oxidative phosphorylation. ATPs will be produced for NADH and for FADH2. Now let's start with this one. We have 2 NADH. The multiplier is 2.5. So you have here a 5 ATP produced from the 2 NADH in pyruvate oxidation. Next, you have 6 NADH produced in Krebs cycle. Multiplier is still 2.5. It's here to remember. And then you will have 15 ATPs here. But the FADH2 here has only a multiplier of 1.5. So 2 times 1.5 is equal to 3 ATPs. So take note that the NADH will always have a 2.5 and FADH will always have a 1.5 inside of pyruvate and Krebs cycle, pyruvate oxidation Krebs cycle. However, the glycolysis may have different kinds of ATPs because it may enter into different pathways. So for example, so that will be a total of 4 ATPs before I forget. So for example here, the 2-NADH as it enters the mitochondrion can go towards pathway number 1, and pathway number 1 has a higher multiplier of 2.5, which means 2 times 2.5 is 5 ATP. So adding everything up, 5 plus 5 is 10, plus 15 is 20, 50, 5 times 5, 5 plus 5 is 10, 25, plus 3 is 28, plus 4 is 32. So the total of the ATPs from the oxidative phosphorylation coming from NADH and FADH would be around 32, going through the first pathway. Now, if we're going to go towards the second pathway, then we will have a smaller amount of ATP because multiplier is 1.5, therefore it becomes 3 ATP. So let's look at that. 3 plus 5 is 8, plus 15 is 23, plus 3 is 26, plus 4 is 30. So the range of the ATP will be 30 to 32. So that will be the answer to that. So the question is, why is the total number of ATP produced not constant? As we have seen a while ago, different pathways of NADH molecule in the glycolysis as it goes through the mitochondrion have different amount of ATPs produced. As shown a while ago, the second pathway has 3 ATPs, while the first pathway would have 5 ATPs. So that's why it's a range of 30 to 32. Okay. Now, what if there will be some mutation? So, for example, a mutation in the glucose. Now, if the glycolysis will have a mutation, then everything that follows will not also function, which means nothing will function, so the total ATP will be 0 if glycolysis will not function at all. How about if the mutation is in the Krebs cycle? So this means all of this will be functional. Pyruvate oxidation will be functional. Oxidative phosphorylation will be functional. So we're just going to remove this portion. So you will have a total of 5 plus 5 plus 3 plus 2 is equivalent to 15 ATP. So that will be some idea of what will happen if there will be mutations in this different stages of the cellular respiration. Okay. Now, if oxidative phosphorylation is the one that is not functioning, even if you have a lot of NADH produced, it will not be able to produce ATPs because this one is not functioning. So you only have 4 ATPs. So total, this one and this one at the substrate level, because oxidative phosphorylation will not be functional. Nothing will come out of the NADH and FADH2. Okay, finally we have here the oxidative phosphorylation. So we were talking about ATPs being produced from NADH, but the question is how? So to simplify everything, just take note that the NADH will be containing electrons. So the electrons will then be released through the electron transport chain, and just like in the light-dependent reaction, as the electron passes through the electron transport chain, hydrogen are being transported to the other side of the double membrane. You see here the hydrogen are being placed here, which means there is now an increased amount of hydrogen, and we know from osmosis that higher concentration will move through lower concentration through a membrane. So the high concentration of hydrogen here will try to find a hole, and that hole is ATP synthase, so it can go to the lower concentration, which is the other side. So that is why as it passes through, the hydrogen passes through here, ATP is being produced. So it is because of the hydrogen being transported on one side of the membrane and then flowing back through the ATP synthase that ATP is being produced. So that is why NADH and FADH are able to produce ATP because their electrons causes hydrogen to pass through the other side, and the high concentration of hydrogen will pass through back towards the ATP synthase, producing ATP. So this portion is called electron transfer chain, and this portion is called chemiosmosis. Now imagine if this will stop, there will be no electron transfer chain. So what will happen is that the hydrogen will not be transported to the other side, and it will not flow toward the ATP synthase. Therefore, ATP will not be produced. And then oxygen will not be able to receive electrons, and the NADH and FADH will not be able to donate their electrons. So everything will stop if the electron transfer chain will be malfunctional. If the ATP synthase here will be the one malfunctional, even if there would be a lot of electrons going here, and then there would be a lot of hydrogen going towards the other side, no ATP will be produced because it won't be able to pass through here. Okay, so that is all about cellular